Thank you very much, and thanks for the invitation to this very nice workshop. So I'm going today to speak about recent work that was done by Étienne Lempereur, Nathanaël Cuvel-Magard at École Normale Supérieure, Florentin Curdoux, and with Eric van den Eyden, who is here. But what you'll see is that I'll be covering themes that were first presented by Johan in his beautiful overall presentation yesterday, and that relates to many of the topics that we've seen in the last 2 days. So the problem, as before, is being able to model probability distribution of very high dimensional data. In the example I'll be taking, these data are images. And we've been, of course, all been very impressed by the ability of these systems to model very structured and complex images, such as bedrooms here. And in terms of applications, the applications in physics are absolutely huge, in particular in statistical physics. And I'll be taking examples from astrophysics, the cosmic web, which is the distribution of mass in the universe, and two-dimensional turbulence. And one needs to keep in mind that if you take the example of turbulence, we can synthesize turbulence signals now, but there's still no models of what is the probability distribution of turbulence. And this is an absolutely beautiful problem that has been open since the first papers of Kolmogorov in the 1940s. It's still an open problem, understand the structure of turbulence and the statistics of turbulence. So the overall problem, of course, is how to estimate and sample this distribution in high dimension. So this is an old problem that has been studied a lot in statistics. And what I'll first begin is with the classic approach that was mentioned by Johan yesterday, namely modeling distribution from moments. And because these moments only provide a limited amount of information, you'll need to define the distribution with a regularization criteria. And the regularization criteria will be maximum entropy, which is a very natural measure in physics. So I'll review first all what is around this strategy, and we'll see the computational difficulties that were already mentioned by Johan yesterday. Then we'll move to this so-called modern approach to sampling, which is essentially based on transport and stochastic interpolant. And there we'll go in the world of the talk of Gabriel, of Johan, and a lot of work that was done previously by Eric. And so the question is it possible to blend both approaches? And I'll show that it's indeed something very natural. If we want to avoid the kind of curse of computation that we are facing when trying to compute maximum entropy distribution, then it's very natural indeed to adopt this point of view of transport. The last part of the talk will be about these moments. So it's interesting because this domain, when let's say, if you think of data analysis in the past, that was called signal processing. And in terms of mathematics, it was essentially a topic of harmonic analysis, first Fourier analysis, then wavelets, and so on. And it's very interesting to see how the whole topic has been moving from a mathematical point of view from harmonic analysis to stochastic PD in high dimension. What I'll show is that harmonic analysis still has a role in this problem, because in all the topics that we've been, or talks that we've been discussing, essentially the key issue was to compute the drift of the stochastic differential equation, in other words, the velocity, and there you have a huge deep network that we don't open, which is doing the job. One of the fundamental questions is to open this deep network and to understand how come it can indeed do the job. And that's where harmonic analysis can potentially help understanding that aspect. And we'll look a bit about that in the last part of the talk. Okay,
So let me begin with the classical approach. So the problem is to generate and sample a probability density of a random vectors given n observation. Now, the way it has been approached in statistics, and that's since the work of Jane in the 1950s, is to say there is certain number of observables that you can compute, which are moments that will be expected value of some nonlinear function of your data, and that you can compute as an empirical sum from independent observation. So you're going to get a vector of moments. Now, that's the constraints that you have on your probability distribution, which of course doesn't uniquely define P. So then, as I said, given this constraint, you want to add some form of regularization on your probability distribution. And one very natural measure to impose that P is a regular distribution is to impose that it has a maximum entropy. So if you try to maximize this concave function under this constraint, which are linear equality over the probability distribution, you can analytically compute the solution with Lagrange multipliers. The Lagrange multipliers will be this vector theta star over there. And you can realize that your probability distribution is going to be the exponential of the linear combination of the moment generating function over there. In other words, you have a Gibbs energy, which is a linear function or a linear combination of all the components of the vector phi of x, which is over there. Now, in physics, theta star is interpreted as coupling parameters, and these kind of models is used all over physics. The fact that you have a maximum entropy means that the system is at equilibrium. And depending upon the type of physics, you will have different type of Gibbs energy over there. Okay, so the framework is very clear, and that's the standard statistical framework that has been around for the last 50 years, essentially. Now, there is still a problem around that. Obviously, how do you want to choose the moment if you are given a set of data and you want to characterize the probability distribution so that this will define a good approximation of your distribution P? Then suppose that phi is known, how to estimate these Lagrange multipliers and how to sample this probability distribution, which has this exponential expression over there. Now, that relates to the problem that were mentioned by Joan yesterday. Essentially, the common wisdom until now was you can't do this in very high dimension if your Gibbs energy is not convex, because it will go through an optimization of a non-convex problem that will take a huge amount of time. So this common wisdom has been very much shaken by all results on deep network. And what I'll be showing here is how you can apply these kind of techniques to indeed get computation which avoids this critical slowing down that is normally observed when you have a non-convex Gibbs energy over there. Okay, so let me move on and try to go a little bit more detail on how you compute this maximum entropy distribution. One result that you can verify quite easily is that if you consider the distribution of exponential distribution whose Gibbs energy are linear combination of the coordinates of phi of x, then the maximum entropy distribution is in fact the distribution which minimizes the Kullback-Leibler divergence between the true distribution and the distribution p theta. So in other words, the expected value relatively to p of log p over p theta. If you separate the log as a difference between two logs, you are going to get two terms over there. The first term is called the likelihood in statistics. It's the expected value or the log likelihood of the log of the probability distribution indexed by your parameter theta. The second term is the minus entropy of P, doesn't depend upon theta. So if your goal is to try to optimize this Kullback-Leibler divergence relatively to theta, you don't care about the second term. So what our standard algorithm is going to do here, you're going to try to minimize this distance, and for doing that, you'll use a gradient descent. Now, in the case where the energy is linear in terms of phi, you can verify that this is going to be a convex quantity as a function of theta. So the gradient descent is guaranteed to converge, and you can compute the gradient of the likelihood relatively to theta. And the gradient of the likelihood relatively to theta will be the difference between the true moments that you've been calculated from the distribution P and the moments calculated from the distribution P theta. And indeed, this is going to be minimum. In other words, the derivative will be 0 when these moments are going to be equal, which is another way to say the maximum entropy distribution, which has the right moment, can be written that way with the appropriate moments over there. So you can compute this gradient. The only difficulty is that you need to compute this expected value. So what does that mean? For each theta, you have a probability distribution P theta, and you need to compute the expected value of phi relatively this probability distribution. How are you going to do it? You will need to sample, in other words, produce sample of the distribution P theta and make a Monte Carlo sum. This means that at each iteration of theta, you need to sample P theta, which requires a lot of computation. So you are back to this problem that mentioned Johan yesterday. The key difficulty there is to sample a probability distribution P theta, which has such an exponential distribution. The way to do it was mentioned by also Johan yesterday. One simple way is to do a Langevin dynamics. In other words, you write a stochastic PD. Essentially, what you do is a gradient descent relatively to the energy. So when you do this gradient descent, you're going to get the grad of the energy, which is the first term over there. So you are going to move your sample in order to reduce the energy by doing a step in the direction of the gradient of the energy, plus some noise. Now, why do you need this noise in order to reach, to sample the distribution? It's because the distribution a priori is non-convex. So the way it's going to go is that you are going, if you have, let's say, one set of local minima over there, another set of local minima over there, the algorithm is going to go down and therefore will have a tendency to go in, if you are in this basin of attraction over there, with some random noise. And then from time to time, with a very low probability, you may jump from one local minima to the other, thanks to the addition of noise over there. And of course, the jump is going to be very unlikely if you have an energy barrier, which is very high, because your Langevin diffusion is going to be there. In order to jump over there, you need to cross this barrier, and that means that you need to have a noise in the right direction and of a sufficient amplitude that allows you to cross the barrier. And that's going to decay exponentially in terms of probability as a function of the barrier height in terms of energy. So essentially, in theory, this algorithm works, but in practice, they don't work, especially in high dimension, because not only you need to cross the barrier, but you need to go exactly in the right direction to cross the barrier, and that gets extremely, extremely unlikely. So essentially, it doesn't work. Hence, this idea that these algorithms are not appropriate in high dimension. Now, there is one way you can cut a little bit the calculation is by avoiding to compute the parameter theta iteratively. And that's an idea that was introduced in the early 2000s. And the idea is to replace the Kullback-Leibler divergence by a Fisher divergence. What is the difference between the two is that here we are going to have a gradient relatively to x. The fact that you have a gradient relatively to x of the log probability means that you are eliminating the normalization constant, and it is the normalization constant which makes it difficult to compute exactly the optimal value of theta. So what you're going to do is to try to look at the difference between the grad of the log of the original distribution minus the one that you are looking for the appropriate theta. Now, in this case, you do an integration by part. You can verify that there is an explicit solution of theta star which minimize the Fisher divergence, which can be calculated from expected value of the gradient of phi by solving this equation. This is the Gram matrix of the gradient of phi. And all this can be estimated directly from sample, so you don't need anymore to go through an iterative process to identify the theta. But there is two caveats here. The first one is that unless the probability distribution you deal with, log of p, is not exactly a maximum entropy distribution. In other words, if you have a model error, then the estimator is going to be biased. In other words, you are not going to get exactly the maximum entropy solution. The second thing is that if you look at this estimator over there, when you replace the expected value by a finite sum over a finite amount of data, it has a huge variance. So that in practice, these kind of estimators have introduced a very large error. Finally, even though you may be able to estimate the parameter, you still need to sample your maximum entropy distribution. And as we just saw, that requires to use a Langevin dynamics, which is very slow to converge. So this is essentially the state of the art in, let's say, 2005 to 2010 about estimating that kind of maximum entropy distribution. Okay, now let's move to this so-called modern approach through transport. So as it was already mentioned, the idea is really quite beautiful, is to do a transport from a Gaussian white noise, in this case, to your data distribution. And this transport, you're going to do it by using a linear interpolant between the two. So here you see the noise, and then you progressively add a linear combination of the signal which progressively appear, and ultimately IT will be equal to x once you reach the time t equal 1. Now, what does that correspond to? That was, again, described in full detail by Gabriel yesterday. You begin from a probability distribution, which is the probability distribution of a Gaussian. And if you look at this probability distribution of the interpolant, it's going to progressively evolve into the final probability distribution of the data. And in between, what you're really going to have is a convolution of this distribution with a Gaussian. In other words, a smoothed version of your distribution. So you are having a very gradual evolution of your distribution. And the key idea of this algorithm is to build a transport of the original distribution into the final distribution through a stochastic PD whose drift is going to be adjusted so that at each time t, xt has exactly the same marginal as yt. In other words, at each time t, the probability distribution of xt is equal to pt. So that's the key idea of these approaches. How do we do it? We saw yesterday the result presented quickly by Gabriel. You can compute both the bias here the two components of the bias. The two components of the bias corresponds. If you put sigma to 0, then you are going to get an ODE, and the bias is essentially going to give you the evolution of the probability distribution. And as was shown by Gabriel, it will be given by this expected value of the evolution in time of the interpolant condition to the value of the interpolant. And the second term over there compensates the drift which is produced by the Brownian motion, which is over there. And this is the score. This is the log of the probability, which can again be written, and that was called the Tweety formula, as an expected value of the signal of the noise given the interpolant. Now, this gradient of the log probability, as well as these bias, have very nice analytical formula, but nobody believed that one could compute them. One has to realize, because very often we present that quickly and then we say, okay, now we have a neural network which is going to estimate that. But one has to realize that this is a function of, let's say, 1 million variables. So we are in very high dimension. And you have the gradient of this function. So estimating the gradient of the log probability at any time t seems almost impossible to do, unless you have a piece of luck and P is an extremely structured function. So the miracle of deep network is that they are able to do it, but it's not very clear for what class of function they can indeed do it and what kind of structure they are exploiting in order to do this kind of estimation. So if you look in the case where the data is finite, which is the usual case, one of the questions that came pretty quickly is whether these images that were produced by this system were beautiful images, but in some sense, some form of memorization of the data with some kind of smart patching of the original data, or whether these algorithms were truly sampling a probability distribution. In other words, are estimating this score with a variance which is relatively small. In other words, whether it depends on the training data or whether it doesn't essentially depend upon the training data. So this question was essentially settled about 3-4 years ago. We looked at this with a colleague who's called Eero Simoncelli at the time, and we were absolutely sure that these algorithms were, in fact, just memorizing. Just memorizing. I mean, who believes that you can have an algorithm which is producing a new face or a new bedroom with all the structure of the bedroom? It looks extremely unlikely. It looks much more likely that what you did is take all the bedroom, take the bed of one bedroom or a piece of bed of one bedroom, put it together with the lamp of another image and so on. You patch everything and you get a new image, but which fundamentally completely depends upon the training data. So that was the question. And we did experiments on this kind of thing with standard neural networks. So this is how the neural networks very often look like for image synthesis. These are called UNets. You put the image in input. It performs a series of convolutions and rectifiers, subsampling, convolutions, rectifiers, subsampling like this. And then there is an upsampling like that. You can think of that as a kind of scale axis. I'll come back a little bit to this aspect. So it's as if you were looking at images at different scale in order to compute the score, which is equivalent to do a denoising. You can think of the output image as a denoised version of the input image. Oops. Okay. So here's the experiments that we've been doing with Zara Zadokai and Florent Tangut. The idea is the following. Is the image produced with your sampler depending upon the training data or not? to check that, what you do is you take your training data and you separate in two pieces. One set of, let's say, an image that you're going to use to train a first neural network, and the other set of images that you are going to use to train a second neural network. And then these two neural networks have seen very different images. Then you use both neural networks in order to sample your probability distribution. And to do that, you begin from the same noise image, then you run your SDE with the same noise each time, but the drift is computed with one neural network or the other neural network. So suppose that your neural network is trained with only one image. You put the noise, and you synthesize from your first neural network, this is the image you get, and the second neural network, this is the image you get. They are very different. Now, you can compare these images with the image that you had in your training set. Now, it's not very surprising that in this case, the image in the training set is exactly the same. In other words, you have just memorized information. Then you can do the same thing with 10 images. Again, the two neural networks are going to synthesize two different images. If you look in your data set, what is the closest image to this one, you'll find it, you just memorize. So the neural net are just very smart memorizers. 100 image, same thing. The two neural network, after running USD, are going to synthesize two different images, which are in fact coming from the database. 1,000 image, it's about the same. 10,000 image, you can see that the images are different, but they begin to be a little bit different from the closest image in the training set. And the idea is, in some sense, you don't have enough memory in your neural network anymore to memorize everything. So you memorize, but something not so good, nothing very impressive. Now, when you go to 100,000 image, something very different happens. The two neural networks synthesize essentially the same image, which are of high quality, which is totally different from the closest image. So what that means is that you got out of the memorization regime, and now you are really estimating a score with two different training sets, and the score are very close. That means that the variance of your estimator of the score is very small, so that indeed they are synthesizing the same image if you begin from the same noise. And you can look at that with different noise, and in each time, if you have enough images, they are going to essentially sample the same image. In other words, you have a very small variance on your estimator. Now, it's interesting because in some cases, if you look, for example, here, there is a slight difference. Because, of course, there is a little bit of variance on your estimator of the score, and that can create instability in the path where you're going to fall in one mode or the other mode if you are exactly in the middle, and one mode could be with glasses, the other mode without glasses, okay? But still, what these things shows is that we need to take these things seriously. The neural networks are indeed estimating a score with a low variance, and this score is very reasonable in the sense that it is generating images which are images of faces. Okay, now there is a very nice result, relatively recent by Tony Bonner, Rudy Urfin, Giulio Biroli, and Marc Mézard, who show that, in fact, the reason why you are getting a score which has a low variance is because during the optimization of the neural network, there is a regularization, an implicit regularization, which is coming in, which is due to the stochastic gradient descent. So at this stage, we understand the fact that we get an estimator. We approximately understand the fact that we get a regularized estimator, but we have absolutely no control on the kind of distribution that is being estimated. Okay, some distribution is being sampled, but we have no idea of what is this distribution, and we have no idea on the statistical precision that we have on this estimation given a set of data. That's where the point of view of maximum entropy is interesting. Because in this framework, which is much more conservative, we understand essentially everything. We understand the statistical precision of the moments, which are calculated with empirical sum over independent realization. And we understand exactly the shape of the probability distribution, which is an exponential distribution, but we can't compute it. So the question is, how can you blend both ideas? And that's the result that was obtained by Étienne Lempereur, Nathanael Cuvel-Magard with Eric van den Eyden. The idea is the following. Essentially, we are going to use the same strategy as the homotopic optimization previously described. The only difference is that we are imposing that we are in a class which is an exponential class. In other words, we know that the energy is going to be of that form. In other words, if you look at the gradient of the log of this distribution, you are going to get something of the type theta star gradient of phi of x. So we know that in your PDE, you are going to have a term which is going to be a vector in a product with grad of phi of x plus the noise. Now, what we want to make sure is that at the end of the path, we guaranteed that these conditions are satisfied. So when time is equal to 1, we want to make sure that the solution x at time t equals to 1 satisfies exactly the moment. Sorry, and we want to do it at time t equal to 1, and we're going to make sure that this is true at any intermediate time. So if you want to compare what we are doing here with what is being done with a standard interpolant, what we impose is that xt has a PDF, a probability distribution, which is exactly the same as IT. So in other words, you impose that all the moments of xt and IT are identical. Here, I'm just imposing that few of the moment, m of these moments are the same. So the condition is much weaker than in the case of stochastic interpolant that you estimate with a gradient, with a neural net. As a consequence, as I said, the PD is going to have a much simpler form. And in this vector over there, you have two terms exactly like in the previous PD. You are going to have one term that is going to impose that the moments are going in the right direction. So you are in a situation where you begin from x0 is equal to I0 is equal to the noise. So what you know is that this is true for t equals to 0. Now you want this to be true at any time. So the only condition that you need to impose is that the derivative are equal for all time. And the condition to have the derivative equal at all time will be given by this control term, which depends upon the derivative of the moment. The second thing is that you need to make sure that the moments are preserved, whatever the level of the noise. And the second term over there is compensating for the drift due to the noise. That's exactly as in the previous equation. So you can view this equation as a simplified form of the previous stochastic equation, which was imposing an infinite number of moments, where in this case, I just impose a finite number of moments. I don't need any more a deep network because I have an explicit formula for this gradient. So as I said, this, in fact, you can verify this corresponds to the score matching estimation of the parameter, and this is what is going to guide the moment values. The proof of this is really 3 lines, because the only thing that you need to impose is that the derivative of the moment is matching the derivative of the interpolation moment to make sure that you match the moment at each time. And if you apply the Ito lemma with a direct calculation, you get that. What is really difficult in this problem is that this theorem supposes that there is a solution to this system of equation. So again, this system of equation, it imposes the evolution of dt as a function of these 2 parameters, but there is something which is a bit more complicated than in the previous case. The 2 parameters, eta t and theta t, they depend upon xt. In other words, you have a linear system of equation that needs to have a solution. So these are called nonlinear Makin-Vaslov stochastic differential equation, and it's often very difficult to guarantee the existence of the solution. The key question is to make sure, in particular, that this matrix doesn't explode. So in that kind of situation, you try and see what it gives. And that's what was done. Now, there is 2 cases where you can control the mathematics of this problem. The first case is when you begin from the right moments. In other words, x0 already has the same moments as x. So if the moments don't move, then you can guarantee that the system of equation has a solution and converges to the maximum entropy solution when sigma increase. In general, for a fixed sigma, what this theorem tells you is that you are going to have the appropriate moments, but you are not guaranteed to have a maximum entropy solution. What is the use of sigma over there? What sigma does, it increases the amount of noise you add in the stochastic differential equation. So what is this going to do? It's going to produce a probability distribution which has the appropriate moment, but whose entropy gets larger and larger as sigma increase. So when sigma goes to infinity, the conjecture is that xt is going to converge to the maximum entropy distribution. This conjecture, I'm going to come back to it. It can be proved in one particular case when the moments don't move, but in general, we don't have the result, but we have the numerics to sustain it. Okay, so the numerical computation of that kind of equation, how does it go? At each step of the equation, you need to compute these expected values. So what you need is to simulate your equation with multiple particles together. In other words, you cannot run it from one single xt. Typically, you are going to run it for 100 or more data xt. At each time, you evolve your xt. At each time, you compute the expected values of all the particles, which are defined an interacting system of particles. You are going to get your parameters, and then you can get the next step. Second thing, as I mentioned, you would like to increase the entropy, which is the amount of noise introduced in the system. But there is a caveat here, is that the discretization in time is going to depend upon sigma. And the larger the noise you introduce, modifying sigma is like dilating time. So the larger sigma, the smaller the time step, so the more computation. So what you need to make sure is that you don't need a huge sigma in order to reach nearly the maximum entropy solution. Okay, so this is a first simple example. Here's a Laplace distribution. So P of x is the exponential of absolute value of x. So here, phi, the moments that you compute is just absolute value of x. And here I look at the log probability of the solution at time 1, and it's going to be 2 straight lines. It's shown over there in dashed line. When you compare to the solution obtained by the SDE. Depending upon the type of noise, you see that when the noise is too small, you have a peak which doesn't exist in the Laplace distribution. And when the noise increases up to 10, you reach finally the Laplace distribution. You can see it by checking the entropy of your solution. The entropy of the maximum entropy solution is over there. It's the Laplace distribution. As you increase sigma, the amount of noise that you introduce in your equation, the solution that you are going to get at the end of time is going to have an entropy which progressively increase and converge to the maximum entropy solution. Now, here is a second example, a bit more complicated, which is bimodeled. So the distribution, which is shown in dashed line over there, has two modes. When you begin with an entropy without enough noise in your SDE, the entropy is going to be much smaller than the maximum entropy solution. It shows by the fact that you are synthesizing a distribution which has two modes which are very much separated. As you increase the entropy, the noise in the SDE, the entropy finally converges to the maximum entropy solution, and the two distributions do converge. So, one of the things that you want in this kind of problem to control is the entropy of the solution, because the problem is to have a maximum entropy solution. You can get a lower bound of the entropy of the solution at time t1, which can be calculated directly from the parameter of the equation. And this lower bound, we are going to use it to control the amount of noise that we need to put in the equation. There is a conjecture also. So essentially, this opens all kinds of mathematical problems. As I mentioned, we don't have a control on the existence of the solution. We don't either have a control on the convergence to the maximum entropy solution, but you can do a computation supposing that there is a solution with a Taylor series decomposition, which indicates that the convergence of the entropy should decay like sigma to the -2, and the convergence of the lower bound to the maximum entropy should decay like sigma to the -2. Now, these are completely hand-waving calculations, no proof. You can try to verify them numerically, and we do observe when you look at the convergence of these quantities when sigma increase on a log-log scale, they do converge like sigma to the power -2, but again, there is really no proof. That's the case in both Laplace and bimodal distribution. Okay, the main idea why we're doing all that is that we want to avoid to have to suffer from the energy gap when you have two modes. So this is the log probability distribution. You have one mode here, another mode here. I'm sorry, the gap beta is not that, but it's the difference between that height, this height and this. Well, if you go from here to here, you have to cross the barrier beta, which is over there. So these are the two types of algorithms. The first type of algorithm that you can try is the Langevin equation. If you use a Langevin equation and you want to cross the gap, the amount of steps of your Langevin equation is going to degrade exponentially like beta, the barrier height. So you can do the experiments with that kind of distribution, and you can count the number of steps of the Mallat, which is the equivalent of the Langevin algorithm, in order to converge with a fixed error, and the number of steps on a log scale is going to grow exponentially with beta. If you do the same thing with this moment-guided distribution, you don't suffer at all from that problem, because you don't try to go from one gap to the other, but you are guided within the to sample the different mode from the homotopic path, which begins from the Gaussian distribution. So essentially, you don't suffer from these gaps or this barrier height in between the different modes. And that's what is shown by this kind of calculation. The amount of calculation in order to sample the distribution is independent from the energy gap. Now, of course, these kind of calculations are in low dimension. So I'm now going to finish by going to the high dimensional case. Okay, so these are the kind of distribution I'm going to look at, which are physical distribution, which are stationary and essentially ergodic. In other words, from one single realization, if you average enough in space, you should be able to compute expected values. So the question here is how to choose the set of moments. Now, what is known in physics on this kind of distribution is that in order to simplify the analysis, you want to look at them at different scale and understand how the structure at one scale and the other scale interact. In other words, what are the kind of correlation of structures when you go across scales? And a lot of model had been defined in order to compute such probability distribution. First Gaussian models by Kolmogorov in the 1940s, then Mandelbrot introduced cascade of energies, but which were very far from producing that kind of structure. And so the kind of question is to understand what moments can be introduced in order to model them. So if you, and that's where we come back to harmonic analysis. If you want to try to understand interaction of scale, the first thing is to separate the information of your field at different scales. How can you separate the information at different scales? By using wavelets. So what is a wavelet? A wavelet is a function which is localized in space here. I have images, and whose real part looks like an oscillatory, let's say, cosine, and imaginary part sine. But the important thing is that these are oscillatory functions which have a local support and a fast decay. And these functions, I'm going to scale them by a factor 2 to a j, so their support are going to grow or shrink, and rotate them in order to measure the frequencies within different direction. And here are the wavelets rotated, rotations like this, and dilated. The wavelet transform is computed by taking your field and making a convolution with the wavelet. So in the Fourier domain, this means that you are going to multiply the Fourier transform of x. So x, again, is the field over there, okay? Think of it as an image. It's not a position variable. That's really important. X is the field, so it's the Fourier transform of x multiplied by the Fourier transform of the wavelet, which is located in a frequency band over there, whose orientation depends upon the orientation of the oscillation. So when you rotate the wavelet, what you essentially do is to rotate the support of the wavelet in the Fourier domain, and you are going to cover an annulus like this. When you dilate the wavelet, you dilate the support in the Fourier domain, and you cover all the annulus, so you are going to cover the whole Fourier plane with all your wavelets. So essentially what this is doing, it's taking your image and it splits it into different frequency bands, which frequency channels, which are these different wavelets, different scale, different orientation. Okay. Now, what you're interested is to understand the interaction. In other words, you can translate that simply as a correlation between different frequency bands, okay, or different orientation. So the first naive idea which comes to mind is to say, well, it should be easy. The only thing I have to do is to try to correlate the information in different frequency bands, okay? In other words, compute the correlation between the wavelet coefficient in one frequency band and in the other frequency band. If you compute this integral with Parseval formula, that's going to be the integral of their Fourier transform. But because the Fourier transform are multiplied by the wavelet, which have different support, these two functions have different support, and so their integral is equal to 0. In other words, you have zero correlation between structures that appears at different scale. It's the same reason why the covariance of a stationary process is diagonalized by a Fourier transform. No correlation across frequencies. That's what you can see here. Here you can see the image. This is the wavelet transform at one scale, and then you can compute it at the next scale and the next scale. These images, they look very similar, but if you correlate them, it's equal to 0 because their phase oscillate at different speed. So when you do the integral vanishes. Two observations. First, they are very sparse. When the image is gray, that means the coefficients are 0. There are few non-zero coefficients. Second, they are not correlated, but they look very similar. So they are very strongly dependent. So if you have a problem which is find moments to characterize such image, that means how to characterize the dependencies of these images at different orientation and different scale, and how to characterize the sparsity of these images. Now, one thing you can do is something very simple to take the modulus of these coefficients, okay? So this is, the modulus of the wavelet coefficient. And what you see appears are edges. And the edges, they are very similar. Oops. They are very similar for the different wavelets and very similar across scale because an edge is an almost self-similar structure. So showing that these things are similar now is much easier because you can just directly do a correlation. You have killed the phase which is responsible for the fact that the correlation is equal to 0. And now the correlation should be informative. So that's what we are going to do. So I remind you, what we want to do is to compute a vector phi of x so that the expected value, the moments, gives you information about the probability distribution of the field you are interested in. And that's what we're going to do with this so-called wavelet scattering transform. First thing, you want to characterize the sparsity. So the sparsity is often characterized by L1 norm. Here, it's going to be the expected value of the absolute value of the wavelet coefficient. We are going to look at the energy within each frequency band of the wavelet coefficients. And last thing, we are going to look at the correlation of the modulus of the wavelet transform. These modulus are themselves multi-scaled structure. So we compute the second wavelet transform over it, and we look at their energy within each frequency band. So these are all the moments that are being calculated. Oops. Here's it. You see, they are completely explicit. If you compare that to a deep network, for example, the deep network that are used to synthesize faces, in the deep network, there was, so it was small image of 80 by 80 pixel. The deep network had 7 million parameters for very small images. Here, the number of parameters which corresponds to the size of this moment vector is going to be much, much, much smaller. But in this case, we design it carefully by really trying to capture the important information. If you have a field of size d, the number of moments is of the order of log d cube, so it's much smaller than the size of the image. This means that you will only need one image to estimate all the moments, whereas in the previous case for faces, I needed 100,000 images in order to have a score that you can estimate with a small variance. So we are in totally different regime. Now, what does it give? In the case of this cosmic web and turbulences, you can generate with these moments, we have exactly 1,200 wavelet moments, again, as opposed to these 7 million moments, parameters, and these images are much more, they are 256 by 256, not 80 by 80, so much bigger. And visually, you can see you get essentially the same distribution. You can check that the probability distribution are very close by looking at bispectrum or trispectrum moments. But essentially, what that shows is that for structure which are relatively simple compared to phases. You don't need to go to deep network. You can completely control the statistics and compute the sampling with the same homotypic technique using an SD in this case. One thing we can compute is also the entropy of these random processes. Now, in the case of physical processes like that, as far as I know, it was not possible to compute their entropy. Here we have now a numerical scheme that allows to exactly compute the entropy of these processes. The way I'm going to present the entropy is through what Schrödinger was calling the negentropy, is not the entropy of the process, but the difference between the entropy of a Gaussian process, which has the same variance, minus the entropy of the process. The advantage is that this quantity is independent from scaling, rotation, or any affine transform on the random process. So we can verify first that as sigma increase, the entropy increase to a maximum. In other words, the negentropy is converging. That's in the case of the cosmic web and in the case of the turbulence. We can verify the conjecture on the decay of the entropy as a function of the variance, and that's going to take 1 minute. I have a, oh no, oh yeah, here's it. This is another example. That's an example from finance. This is the S&P. This is the S&P which was generated from exactly the same kind of wavelet moments. So these are increment of the price of Standard & Poor. You compute the wavelet moments from this, and then you generate a new financial time series which has a maximum entropy relatively to these moments by solving this stochastic PD. Now, the amount of noise that you need to put in the PD in order to reach the maximum entropy is always of the order or 5 or 10. And you can see it by the fact that as long as the noise doesn't reach that level, the negentropy decrease. In other words, the entropy is still increasing. You can compute the negentropy in this case. Oh, one comment I forgot to make in the previous case. If you look at the two images, the turbulent flow and the cosmic web, there is one which is much more structured than the other. And the one which is much more structured is the the turbulence flow, because it has, if you follow the line of flows, they follow very regular geometric curves. In the case of the cosmic web, the level set of the image are extremely regular. That you can check by looking at the negentropy, which is much larger. In other words, the turbulence is a structure which is much less Gaussian than a cosmic web. In this case, the negentropy is even much smaller, which indicates that these kind of random processes are even much closer to Gaussian. In fact, in finance, by default, the kind of models that people use are Brownian motion, Gaussian. Clearly, there is a difference with Gaussian. You can see it from this burst of energy, which is captured by this negentropy, which is non-zero. And this is why you can resynthesize processes which also have these kind of structures. Okay, that's the convergence of the entropy. You can check also the fact that it's really important to have a maximum entropy distribution by looking at what people in finance call the rolling volatility. At any time in a financial market, people try to measure how much the price are varying. How do they measure that? By looking at the variation of the price over the last 4 or 5 days, okay? This is what they call the rolling volatility. So the variation of the market values at a given time. And you can look at these histograms. If you make a model with these stochastic differential equation which reproduce the moments but don't maximize the entropy, then you get a distribution of rolling volatility, which is very different from the distribution of the true market. If you increase the volatility of the stochastic differential equation to reach the maximum entropy, then you have a model which is almost the same as the distribution of rolling volatility of the true data. So that shows that these models of maximum entropy really do make sense in all these kind of random processes. It makes sense, given the constraint, to try to have a very regular distribution which maximizes the entropy. Okay, let me finish on that. So the conclusion on this is, first, these ideas of modeling probability distribution through a transport are really completely generic. Beyond neural network, they are now completely key tools in statistics to synthesize any probability distribution in high dimension, because they avoid the critical slowing down that occurs when you have a non-convex energy. So these are really now very important tools that you can apply almost everywhere. In this case, we've been applying it to these finite moment models with maximum entropies. The interesting aspect of these models is that they are mathematically much simpler than the models where you try to reproduce the whole probability distribution. In some sense, there are particular cases of these problems where you impose an infinite number of moments. So we believe that it's one way to try also to understand a bit better the statistics of the infinite moment case, where you can impose all the marginal probability distribution. One really important question is to understand whether we can go beyond these stationary model of physical images such as turbulence or cosmic web by prescribing mathematically the moments. In other words, can we synthesize faces with some kind of harmonic analysis tools? It looks hopeless, but there are some numerical experiments that show that it may not be as hopeless as that. At least that's one open question now. And I think that these type of questions are now very important, because the mathematics which are outside the deep networks are now getting very much refined and well understood with these diffusion models. What is really not understood is what's happening inside, and that goes in the direction of the talk that Lenka was doing. Understanding how it computes a score, which is equivalent, the score again is the gradient of the log probability, which is in some sense equivalent to understand how it learns this function phi of x, which I impose, but which in the case of a deep network is itself being learned, is a totally open question. And for any PhD student, that's an interesting problem. Thanks very much.